Ladies and gentlemen, imagine a moment when thought no longer waits for movement, when intention becomes action without delay. We are standing at the edge of a transformation where technology does not sit in your hands or on your desk, but works in harmony with the human mind itself. This is not science fiction, not a distant future, but a real step forward happening now, where engineering, biology, and intelligence converge to redefine what humans can do, how we heal, and how we connect with the world. Stay with me, because what comes next changes everything. And the beginning of human trials marks a pivotal step in the pursuit of technologies that expand human capability through seamless integration with advanced engineering. This moment represents years of disciplined iteration, first principles thinking, and a commitment to solving problems that sit at the intersection of biology, software, and hardware. At its core, this effort is driven by the same philosophy that guides transformative work in electric mobility, autonomous systems, and large-scale energy solutions. Identify the fundamental constraints, rethink them from the ground up, and build systems that are not only functional, but scalable, safe, and capable of continuous improvement. And human trials signal a transition from theoretical validation to real-world interaction. This shift requires an uncompromising focus on safety, reliability, and precision. Every component involved, from microscale materials to embedded software, must operate in harmony with the human nervous system. The approach emphasizes designing devices that work with the body rather than against it, respecting biological limits while extending what is possible. This reflects a broader engineering mindset that prioritizes elegant solutions over complexity, reducing friction wherever possible to enable more natural interaction between humans and technology. And the underlying objective is to create a high-bandwidth interface between the brain and machines. Traditional methods of communication, such as keyboards, touch screens, or voice input, are limited by physical motion and sensory translation. A direct neural interface has the potential to dramatically reduce latency and increase information transfer, enabling new forms of interaction that feel intuitive rather than learned. This aligns with a long-standing vision of technology as an extension of human intent, where tools respond instantly and accurately to thought, not effort. And from an engineering perspective, achieving this requires breakthroughs in miniaturization, power efficiency, and data processing. Devices must be small enough to integrate seamlessly, consume minimal energy, and operate for extended periods without maintenance. Manufacturing processes must be refined to produce consistent, high-quality components at scale. These challenges mirror those faced in the development of advanced batteries, high-performance chips, and autonomous hardware, where success depends on relentless optimization across every layer of the system. And human trials also represent a critical feedback loop. Simulation and animal testing can validate concepts, but real-world use provides insights that cannot be replicated elsewhere. Data gathered during these trials informs iterative design, allowing engineers to refine both hardware and software based on actual performance. This process of rapid learning and continuous deployment is a cornerstone of modern technological advancement, enabling systems to improve exponentially over time rather than incrementally. And the potential applications extend far beyond initial use cases. Restoring lost neurological function is an important starting point, offering hope to individuals affected by paralysis, sensory loss, or neurological disorders. Over time, the same platform could enable broader enhancements, such as improved memory, recall, accelerated learning, or more immersive interaction with digital environments. Each application builds on the same foundational architecture, reinforcing the importance of designing flexible, upgradable systems from the outset. And ethics and responsibility are integral to this phase of development. Human trials demand transparency, rigorous oversight, and a commitment to participant well-being. Building trust is essential not only with trial participants, but with society at large. The technology must demonstrate clear benefits, measurable safety, and a path toward equitable access. This mirrors the responsibility taken when deploying autonomous systems or large-scale energy infrastructure, where public confidence is earned through performance accountability and consistent results. And the convergence of artificial intelligence and neural interfaces is another defining aspect of this milestone. Advanced algorithms are required to interpret neural signals accurately and translate them into meaningful actions. These systems must adapt to individual users' learning patterns and adjusting in real time. This adaptive intelligence is similar to the learning systems used in autonomous driving, where continuous data input refines decision-making and enhances safety. In both cases, the goal is to create systems that improve with use, becoming more precise and reliable over time. And scalability remains a central consideration. A successful human trial is not an endpoint, but a foundation for broader deployment. This requires designing manufacturing pipelines, software update mechanisms, and support systems that can grow alongside demand. Lessons learned from scaling electric vehicles and energy storage solutions inform this process, demonstrating that innovation must be paired with operational excellence to achieve meaningful impact. And the broader implication of beginning human trials lies in redefining the relationship between humans and technology. Rather than viewing machines as external tools, this work explores a future where technology becomes a natural extension of cognition. Such a shift has profound implications for productivity, creativity, and problem-solving, enabling individuals to engage with complex systems more directly and effectively. It reflects a belief that the greatest advancements come from empowering people, not replacing them. And this moment also underscores the importance of long-term thinking. Developing neural interfaces is not a short-term endeavor. It requires patience, resilience, and a willingness to tackle challenges that may take years to resolve. The decision to move into human trials reflects confidence in the underlying technology and a readiness to learn from real-world application. It embodies a mindset that prioritizes progress over perfection, understanding that meaningful breakthroughs emerge through iteration and persistence. And as human trials begin, the focus remains on building a system that is safe, adaptable, and capable of evolving alongside advances in computing and materials science. Each trial contributes to a growing body of knowledge, guiding future development and informing responsible deployment. The emphasis is not on spectacle, but on substance, measured progress, validated performance, and a clear trajectory toward technologies that enhance human potential through thoughtful, disciplined engineering. And this disciplined approach demands an ecosystem mindset where progress in one domain accelerates advancement in others. Materials science informs biocompatibility and durability, while semiconductor innovation enables faster, more efficient signal processing. Advances in robotics contribute to surgical precision, reducing invasiveness and improving consistency. Software architecture ensures that data flows securely and reliably, supporting both real-time interaction and long-term learning. Each discipline reinforces the others, creating a system that is greater than the sum of its parts and capable of evolving as new discoveries emerge. And human trials also redefine how validation is understood. Success is not measured solely by technical performance, but by how naturally the technology integrates into daily life. Comfort, usability, and adaptability become as important as accuracy and speed. This user-centered philosophy has guided the development of other transformative products, where the ultimate benchmark is not laboratory metrics, but real-world experience. When technology fades into the background and intent comes to the foreground, true progress has been achieved. And the data generated during these trials carries immense value. Neural signals are complex, dynamic, and deeply personal, requiring systems that can interpret subtle patterns without imposing rigid assumptions. Machine learning models must be trained to recognize intent amid noise, adapting to changes over time as the brain itself evolves. This adaptive capability mirrors the continuous improvement seen in intelligent systems across transportation and energy, where performance increases as more data is gathered and analyzed. The emphasis remains on building systems that learn responsibly, respecting privacy while unlocking insight. And safety remains a non-negotiable principle throughout this phase. Redundancy fail-safes and rigorous testing protocols are embedded into every layer of the design. Hardware is engineered to withstand long-term use while software is monitored continuously to detect anomalies before they become issues. This proactive approach reflects a broader commitment to engineering systems that anticipate risk rather than react to failure. Trust is built through consistency, transparency, and a demonstrated willingness to address challenges head-on. And as trials progress, collaboration becomes increasingly important. Progress in this field requires close coordination between engineers, clinicians, researchers, and participants. Each perspective contributes to a more complete understanding of how the technology performs and how it can be improved. This collaborative model has proven effective in tackling complex challenges, from scaling manufacturing to deploying autonomous systems in diverse environments. By integrating feedback across disciplines, development accelerates while maintaining alignment with real-world needs. And the implications for accessibility are significant. A core objective is to ensure that advanced neural technology does not remain limited to a small population, but can be produced and deployed at scale. This requires cost-efficient manufacturing, streamlined deployment processes, and robust support infrastructure. Lessons learned from scaling other advanced technologies demonstrate that affordability is not achieved by compromise, but by design. Efficiency, simplicity, and vertical integration enable high performance without prohibitive cost. And interoperability is another key consideration. Neural interfaces must coexist with a rapidly evolving digital ecosystem, integrating seamlessly with existing platforms while remaining adaptable to future innovation. This requires open architectures that support updates and enhancements without requiring invasive changes. The ability to improve functionality through software updates extends the lifespan of the hardware and ensures that users benefit continuously from advancements in computation and artificial intelligence. And the beginning of human trials also invites broader societal dialogue. As technology moves closer to the core of human experience, questions about agency, identity, and responsibility become increasingly relevant. Addressing these questions requires clarity of purpose and a commitment to ethical deployment. The guiding principle remains empowerment, enabling individuals to overcome limitations and engage more fully with the world. By focusing on tangible benefits and measurable outcomes, the technology earns its place as a tool for progress rather than disruption. And the pace of development reflects a balance between urgency and caution. There is recognition that the potential benefits are profound, but also an understanding that progress must be deliberate. Each iteration builds on validated learning, ensuring that advancement is sustainable rather than rushed. This measured approach has been essential in other high-stakes domains where reliability and trust are prerequisites for adoption. Moving fast does not mean skipping steps. It means optimizing every step through rigorous analysis and execution. And human trials also serve as a proving ground for manufacturing and deployment processes. Producing devices that meet stringent quality standards at scale requires precision and repeatability. Automation, quality control, and supply chain integration are refined in parallel with product development. This operational focus ensures that success in trials can translate into broader availability without compromising standards. It reflects a belief that innovation must be supported by execution to achieve real-world impact. And as understanding deepens, new use cases emerge organically. Initial applications inform subsequent ones, revealing possibilities that were not apparent at the outset. This organic expansion mirrors the evolution of other platforms that began with focused goals and grew into versatile ecosystems. By maintaining a flexible foundation, the technology can adapt to diverse needs, from medical applications to enhanced interaction with digital environments. And the integration of neural interfaces with intelligent systems opens pathways for more natural collaboration between humans and machines. Rather than issuing commands, users can express intent, allowing systems to respond proactively and contextually. This shift has implications for productivity, creativity, and problem-solving, enabling individuals to engage with complex systems more intuitively. It reflects a vision of technology that augments human strengths rather than dictating behavior. And each step forward reinforces the importance of long-term vision. Developing technology that interfaces directly with the human brain requires patience, resilience, and a willingness to confront uncertainty. Challenges are expected and setbacks are treated as data rather than failure. This mindset has driven progress across multiple industries, enabling breakthroughs that once seemed unattainable. By maintaining focus on the underlying mission, development remains aligned even as details evolve. And the expansion of human trials also emphasizes the need for robust education and communication. As capabilities grow, so does the responsibility to explain them clearly and accurately. Misinformation can undermine trust, while transparency fosters informed engagement. Clear communication about goals, limitations, and progress ensures that stakeholders remain aligned and supportive. This openness has been essential in building confidence around other transformative technologies. And the trajectory established by these trials points toward a future where boundaries between biological and digital systems become increasingly fluid. This convergence is not about replacing human experience, but enhancing it through tools that respond to thought with precision and care. By grounding innovation in first principles and disciplined execution, the technology evolves responsibly, guided by evidence rather than speculation. Each iteration refines understanding, bringing the vision of seamless human-machine integration closer to practical reality. And as trials continue, attention remains fixed on incremental improvement. Small gains compound over time, transforming early prototypes into robust platforms. This compounding effect has driven progress across multiple domains, demonstrating that persistence and focus can yield exponential results. By embracing iteration and learning, development stays adaptable, capable of responding to new insights and emerging challenges without losing momentum. And the work underway reflects a broader commitment to expanding what is possible through engineering excellence. Human trials are not an endpoint, but a catalyst, accelerating learning and shaping future development. Every insight gained informs the next step, reinforcing a cycle of innovation that prioritizes safety, scalability, and impact. Through this process, technology moves closer to fulfilling its potential as a natural extension of human capability, guided by data integrity and an unwavering focus on building systems that serve humanity. And this expanding cycle of innovation reinforces the importance of alignment between ambition and execution. As systems grow more capable, maintaining coherence across hardware, software, and human factors becomes increasingly complex. Precision in design must be matched by precision in deployment, ensuring that each update, adjustment, and improvement integrates smoothly into the existing framework. This level of coordination is achieved through rigorous testing, disciplined processes, and a culture that values clarity over convention. When complexity is inevitable, simplicity becomes a competitive advantage. And the relationship between neural interfaces and artificial intelligence continues to deepen as trials progress. Algorithms do not merely decode signals, they adapt alongside the user, forming a dynamic partnership that evolves with experience. This co-adaptation requires models that can learn quickly while remaining stable, balancing responsiveness with predictability. Such systems are designed to improve not through dramatic leaps, but through continuous refinement, where each interaction contributes to a more accurate understanding of intent. Over time, this creates an interface that feels less like a device and more like a natural extension of cognition. And latency reduction remains a critical focus. The closer a system approaches real-time response, the more intuitive it becomes. Achieving this requires optimization across every layer, from signal acquisition to processing and output. Hardware must capture neural activity with high fidelity, while software pipelines process data efficiently without sacrificing accuracy. These constraints echo challenges faced in other real-time systems where milliseconds matter and reliability is paramount. By addressing latency holistically, the technology moves closer to seamless interaction. And energy efficiency is equally essential. Devices that operate within the body must function reliably over extended periods with minimal power consumption. Advances in low-power electronics, energy management, and materials science converge to address this challenge. Each incremental gain in efficiency extends operational lifespan and reduces maintenance requirements, improving usability and safety. This emphasis on efficiency reflects a broader philosophy that sustainable performance is achieved through thoughtful design rather than brute force. And the surgical aspect of deployment benefits from automation and precision robotics. Consistency in placement and minimal invasiveness reduce risk and improve outcomes. By integrating robotics with advanced imaging and planning software, procedures become more predictable and scalable. This approach mirrors broader trends in manufacturing and automation, where precision and repeatability enable quality at scale. Translating these principles into clinical settings represents a significant step forward in deployment strategy. And as trials expand, the diversity of participants provides valuable insight into variability across individuals. Neural patterns differ, and systems must accommodate this diversity without extensive customization. Adaptive algorithms and modular design allow the platform to adjust to individual differences while maintaining a standardized core. This balance between personalization and scalability is central to achieving widespread adoption. Designing for variability from the outset ensures resilience as the user base grows. And the feedback loop between users and engineers becomes increasingly refined. Direct observation, data analysis, and qualitative feedback inform rapid iteration. This iterative cycle shortens development timelines while improving quality, as issues are identified and addressed early. The willingness to learn from real-world use rather than relying solely on theoretical models accelerates progress and grounds innovation in practical reality. And security and data integrity remain foundational concerns. Neural data is uniquely sensitive, requiring robust safeguards against unauthorized access or misuse. Encryption, secure processing environments, and strict access controls are embedded into the system architecture. Protecting user data is not an afterthought, but a core design requirement, reinforcing trust and ensuring long-term viability. This commitment to security parallels efforts across other connected technologies, where resilience against threats is essential for sustained adoption. And the platform nature of the technology becomes more apparent with each iteration. A stable core supports a growing ecosystem of applications, enabling developers and researchers to explore new possibilities. This extensibility fosters innovation beyond initial use cases, creating opportunities for collaboration and discovery. By providing a flexible foundation, the system encourages experimentation while maintaining safety and reliability. And integration with external devices and digital environments continues to evolve. Seamless communication between neural interfaces and existing platforms expands functionality without adding complexity. This interoperability ensures that users can benefit from advancements across the broader technology landscape rather than being confined to a closed system. Open standards and modular interfaces support this integration, enabling continuous enhancement through software updates. And the learning curve for users is intentionally minimized. Intuitive design reduces the need for extensive training, allowing individuals to focus on outcomes rather than mechanics. When technology aligns with natural behavior, adoption accelerates and satisfaction increases. This user-centric approach has proven effective across multiple domains, reinforcing the principle that the best technology feels effortless. And as confidence grows, regulatory engagement becomes more collaborative. Transparent communication, rigorous documentation, and evidence-based validation support constructive dialogue. This collaborative approach ensures that safety standards evolve alongside innovation rather than lagging behind. By working proactively with oversight bodies, deployment pathways become clearer, and more predictable, benefiting both developers and users. And manufacturing refinement continues in parallel with technical development. Yield improvement, quality assurance, and supply chain optimization reduce cost and variability. Vertical integration enables tighter control over critical components, ensuring consistency and reliability. These operational improvements are essential for transitioning from limited trials to broader availability without compromising standards. And the cumulative effect of these efforts is a system that improves not only through technological advancement, but through organizational learning. Each challenge encountered informs better processes, stronger designs, and more resilient strategies. This learning culture sustains momentum, enabling progress even in the face of complexity and uncertainty. And as neural interfaces mature, their role within the broader technological ecosystem becomes clearer. They act as a bridge between human intent and digital capability, enabling more direct and expressive interaction. This shift has implications across fields from healthcare to creative work, where reduced friction unlocks new possibilities. By focusing on foundational capability rather than narrow applications, the technology remains adaptable to future needs. And the emphasis on long-term impact guides decision-making at every stage. Short-term gains are weighed against durability, scalability, and ethical responsibility. This perspective ensures that development remains aligned with broader goals, avoiding compromises that could limit future potential. Building for longevity requires discipline, but it also creates the conditions for sustained progress. And the iterative nature of human trials reinforces the value of patience. Breakthroughs emerge from accumulated insight rather than singular moments. Each iteration refines understanding, reduces uncertainty, and expands capability. This gradual progression reflects a commitment to doing the work thoroughly, recognizing that transformative change is built through persistence. And the convergence of engineering rigor, user-centered design, and ethical consideration defines this phase of development. By maintaining balance across these dimensions, the technology advances responsibly, earning trust through performance and transparency. Each step forward strengthens the foundation for subsequent innovation, ensuring that progress remains grounded in evidence and experience. And as the system continues to evolve, attention remains focused on reducing barriers between thought and action. By aligning technology more closely with human intention, new forms of interaction become possible. This alignment is not about replacing existing tools, but about enhancing them, creating a more fluid and responsive interface between humans and machines. And the ongoing expansion of trials serves as a catalyst for deeper understanding and broader collaboration. Insights gained inform not only this platform, but adjacent technologies, creating a ripple effect across innovation efforts. By sharing knowledge responsibly and building on validated learning, progress accelerates while maintaining integrity. And the work underway reflects a belief that the most meaningful advancements emerge from disciplined execution and continuous learning. Each challenge encountered becomes an opportunity to refine approach and strengthen outcomes. Through this process, technology moves steadily toward a future where human capability is amplified through thoughtful, precise, and scalable engineering. And this amplification of capability continues to shape how progress is evaluated and prioritized. Performance is no longer judged solely by isolated benchmarks, but by how effectively the system adapts to complexity over time. The measure of success becomes resilience, the ability to operate consistently under varied conditions, learn from anomalies, and improve without requiring constant intervention. This emphasis on robustness mirrors principles applied in other mission-critical technologies, where reliability is achieved through foresight, redundancy, and disciplined iteration. And as deployment scenarios diversify, environmental factors gain prominence. Variations in lifestyle, activity level, and external conditions introduce new variables that the system must accommodate gracefully. Designing for these realities requires flexibility at both the hardware and software levels. Sensors must maintain fidelity across contexts, while algorithms adjust dynamically to shifting inputs. This adaptability ensures that performance remains stable, reinforcing confidence in everyday use. And the integration of feedback mechanisms becomes increasingly sophisticated. Real-time monitoring enables systems to assess their own performance and make adjustments proactively. This self-awareness reduces the need for manual recalibration and enhances safety by identifying potential issues early. Such mechanisms reflect a broader trend toward autonomous optimization, where systems are designed to maintain peak performance with minimal external oversight. And as understanding deepens, the importance of standardization becomes clear. Establishing consistent interfaces, protocols, and testing methodologies accelerates development and reduces friction. Standardization does not stifle innovation. It provides a stable foundation upon which innovation can flourish. By aligning around shared principles, teams can focus on advancing capability rather than resolving incompatibilities. And the human dimension remains central throughout this evolution. Empathy informs design decisions, ensuring that technology serves real needs rather than abstract ideals. Observing how users interact with the system reveals opportunities to reduce cognitive load and enhance comfort. Small refinements in ergonomics and interaction can yield disproportionate gains in satisfaction and effectiveness, reinforcing the value of attention to detail. And as trials continue, longitudinal data offers insight into long-term performance and adaptation. Observing how systems and users co-evolve over extended periods informs strategies for maintenance, upgrades, and support. This long-term perspective ensures that design decisions account for durability and life cycle management, reducing obsolescence and maximizing value. And the role of simulation remains significant even as real-world data accumulates. High-fidelity models enable testing of scenarios that may be impractical or unethical to explore directly. By combining simulation with empirical data, development teams can explore edge cases and stress conditions with greater confidence. This hybrid approach accelerates learning while maintaining safety. And cross-disciplinary innovation continues to drive progress. Breakthroughs in one field often unlock opportunities in another, creating momentum that extends beyond the original scope. Advances in materials enable more efficient sensors, which in turn support more accurate algorithms. This interconnectedness underscores the importance of maintaining openness to ideas and collaboration across domains. And as systems mature, the emphasis shifts toward refinement rather than reinvention. Incremental improvements compound, transforming early concepts into reliable platforms. This steady progression reflects an understanding that enduring impact arises from sustained effort rather than sudden disruption. By focusing on fundamentals, development remains grounded even as capabilities expand. And the scalability of support infrastructure becomes increasingly important. Training resources, diagnostic tools, and maintenance protocols must evolve alongside the technology. Investing in these systems ensures that users receive consistent experience and support, reinforcing trust and adoption. Operational excellence becomes as critical as technical innovation. And cultural considerations also influence deployment strategies. Attitudes toward technology vary across regions and communities, shaping expectations and acceptance. Engaging thoughtfully with these perspectives informs communication and design, ensuring that technology is introduced respectfully and responsibly. Sensitivity to context strengthens alignment between innovation and societal values. And as data volumes grow, advanced analytics play a larger role in guiding decision-making. Identifying patterns across large datasets reveals insights that inform prioritization and resource allocation. This data-driven approach reduces reliance on intuition alone, enabling more objective assessment of progress and impact. And the architecture of continuous improvement becomes embedded within the organization. Processes are designed to capture learning systematically, ensuring that insights translate into action. This institutional learning sustains momentum, enabling adaptation even as personnel and circumstances change. And as neural interfaces become more capable, their interaction with other intelligent systems grows more seamless. Collaboration between platforms enables more holistic solutions where capabilities complement rather than compete. This ecosystem approach maximizes value by leveraging strengths across technologies. And the emphasis on transparency continues to shape engagement with stakeholders. Clear communication about capabilities, limitations, and progress fosters informed participation. Openness invites constructive feedback, strengthening outcomes and building credibility. Trust becomes a shared asset cultivated through consistency and accountability. And as the boundary between research and application narrows, the pace of iteration accelerates. Insights move more quickly from observation to implementation, shortening feedback loops. This agility enables rapid response to emerging challenges while maintaining alignment with long-term objectives. And the commitment to safety evolves alongside capability. New features introduce new considerations, requiring continuous reassessment of risk. Safety frameworks are updated iteratively, ensuring that protection scales with complexity. This proactive stance reinforces confidence as systems become more integrated into daily life. And the refinement of user interfaces remains an ongoing focus. Subtle adjustments in feedback, responsiveness, and control can significantly enhance usability. By prioritizing clarity and intuitiveness, the technology remains accessible even as underlying complexity increases. And as experience accumulates, benchmarks for success are recalibrated. What once represented a breakthrough becomes a baseline, prompting renewed ambition. This upward shift reflects a culture that values progress without complacency, continually redefining what is possible. And the interplay between autonomy and user control is carefully balanced. Empowering users requires giving them agency without overwhelming them. Designing interfaces that offer flexibility while maintaining simplicity ensures that control remains intuitive. This balance enhances confidence and satisfaction. And as systems gain capability, their role in augmenting human potential becomes more evident. Reduced friction between intention and action enables new forms of expression and problem-solving. This augmentation is guided by respect for human agency, ensuring that technology remains a tool rather than a determinant. And the cumulative impact of these efforts extends beyond individual applications. Lessons learned inform broader innovation strategies, influencing how complex systems are conceived and deployed. This cross-pollination accelerates progress across domains, amplifying the value of each insight. And as development continues, attention remains focused on fundamentals. Precision, reliability, and scalability guide every decision. By adhering to these principles, the technology advances, steadily capable of adapting to future challenges without losing coherence. And the ongoing expansion of trials reinforces the value of perseverance. Progress emerges through sustained effort informed by data and experience. Each iteration strengthens understanding, enabling more confident steps forward. And this steady advancement reflects a belief that meaningful change is built through alignment of vision and execution. By maintaining focus on core objectives, while remaining adaptable, development continues to move forward, unlocking new possibilities through disciplined engineering and thoughtful integration.